All right, so one of the things that I meant to mention in the last video is when we look at the percentage of deuterium abundance in the universe, like in any direction at all, I can look in any direction, I can look in any distance whatsoever, we get this nice, consistent relative percentage of deuterium. All right, so that this is a huge indicator of that what happened in the early universe, that we do understand our ideas, our theories about what happened in the early universe leads to the correct that we're on to something, in other words. Also the helium, if we look in any direction, we find, of course, the amount of helium is at the very least 25% helium, right? In fact, we don't even find any situations where if you can see individual stars, if the galaxies are close enough that we can see individual stars, the amount of helium is always more than 25%. And even when we look out into the globular clusters, which are ancient, right? The globular clusters are at least 10 billion years old. There was still some stars that underwent fusion, the fusion process, and so helium was created from hydrogen, right? So remember, we can't distinguish between the helium that was created during regular, stellar fusion and the primordial helium. But the thing that we can say is when we look out into the universe, we don't see any epoch in time where there's less than 25% helium, because the amount of helium that was created was created very, very early in the universe, when the universe was very tiny and it was created everywhere, right? So the same amount of, like, in other words, you don't look in any particular direction and just see, something like I'm making this up, but you see galaxies in one particular direction where you'd only see like 17% helium. You always see at least 25% helium. All right, so and this is exactly why. Okay, so this is what when you see the amount of the amount of helium in the universe, there should be during the time when hydrogen and helium were formed in the early universe, about 1/4 of that formation was in the form of helium. So that kind of puts a minimum ratio of the helium that you find out there, in the stars and in the galaxies. Which we never find, we never see situations where there's less than 25% helium. All right, so here's the thing about the deuterium that I was mentioning earlier. So the deuterium, of course, is a nice tool that astronomers use, because the deuterium really just comes from the Big Bang, or just slightly after the Big Bang. So what we say is that's primordial hydrogen and primordial helium, right? I'm sorry, primordial hydrogen and primordial deuterium. Certainly, there's plenty of primordial helium out there, but again, we can't distinguish the primordial helium from the from just normal stellar helium that where hydrogen is turned into helium inside of a star, which is the normal process that goes on every single day. So the amount of deuterium that we find is really is something that allows us to set the amount of just ordinary matter, the amount of density that we find in the universe. All right, so what this is saying, of course, it has to do with this idea of the critical density and the expansion of the universe, the average expansion of the universe, and showing that indeed the universe is flat, not this curve obviously, but this amount. So let's see, this is the present day amount of deuterium and the present day density. So both of them make this nice agreement experimentally and theoretically with the amount of deuterium that we find out there in the galaxies. All right, so there's actually a little bit of a question that involves this thing called the cosmic horizon. Okay, so when we go out to roughly 14,000 megaparsecs, all right, so in any direction at all, this is like the most distant things that you can possibly see, because before that, the universe, there's a time where the cosmic background radiation was so intense that basically we can't see beyond that, right? Remember the point where decoupling takes place. Okay, so decoupling is the point where the universe is cool enough for photons to start traveling around, and those initial photons, of course, during the decoupling epoch, right? So this is actually a really important thing in cosmology is this decoupling. That's the time where photons are actually able to freely travel around the universe without being almost immediately absorbed. So I mean, of course, photons get absorbed. That's perfectly, that happens, obviously. But what took place during decoupling is the universe, of course, has cooled, and by the way, this 14,000 megaparsecs that's the cosmic horizon right now. Okay. During decoupling, when decoupling took place, of course, the universe was much smaller, and of course, the Earth didn't exist. But this idea of decoupling is, when photons, it's basically when the cosmic background radiation existed. Okay, of course, there was cosmic background radiation before that, but at that point, there was the matter and the cosmic background radiation were intermixed. This point, we estimate, is roughly 400,000 years after the Big Bang. It's to be more precise, we use 400,000 years or so after the Big Bang in this book. A little bit more precisely, it's about 380,000 years after the Big Bang. That's the point when decoupling takes place, and there's lots of important stuff. The background radiation is actually right around the visible part of the spectrum, or in the actually, I think it's either in the visible spectrum or in the ultraviolet. And remember, so the universe is expanding and cooling, and so when decoupling takes place, the universe is roughly 3,000 Kelvin. Okay, so that's an important temperature. So we in fact we know what the wavelength of the cosmic background radiation was at that time. So this remember, this is roughly 400,000 years after the Big Bang. The photons are able to travel, and they're so this is everywhere. It's exactly the same, right? You get the same photons everywhere in the universe. And that's, of course, the cosmic background radiation. Now, of course, it's because the universe has expanded, during the time since those photons first started traveling throughout the universe, these have been greatly redshifted, right? They're redshifted now into the microwave region from the just beyond the visible to now right about in the at 1 millimeter or so in the microwave region. All right, so that's actually a really important point for the universe. When it's basically the point where there's light that can travel throughout the universe, right? And so that light that is everywhere the same is, of course, what Penzias and Wilson first detected in 1964 with their feed horn antenna in New Jersey. That was the echo of the Big Bang, and that was the time of decoupling. All right, so here's a problem. They call it the horizon problem, which turns out to not be a problem if we assume inflation. So that's why this is all about inflation. The idea of inflation took place in the 1980s, I think it was. There was a guy from MIT that first came up with the idea, and then some other people came up with I think that's what happened is. They also came up with the idea roughly about the same time. Anyhow, it's that doesn't matter that much. But this idea of inflation takes care of what's called the horizon problem. So when let's say that you look in this direction at B, galaxy B, and then you look in this direction at galaxy A. So the problem is, so in these two opposite directions, 180 degrees apart in the sky, the Earth, when the cosmic background radiation gets to the Earth, it appears exactly the same. But when the cosmic background radiation started traveling, there still hasn't been enough time for information on in this region A to reach region B. It's just barely had time to reach the Earth, which is now in existence. But when the photons first started traveling towards the Earth, our whole Milky Way wasn't even in existence yet. Certainly not our solar system. But anyhow, there's been no contact between point A and point B. So how is it that point A and point B have basically the exact same cosmic background radiation? Why is that? And so that's what's called the horizon problem. All right, and of course this is what inflation solves. Also, there's this flatness problem, and basically for the universe to have, as it says here, has survived as long as it has, the density in the early universe had to be really close to being, the critical density. And there, there's very little room for variation for the universe to be the way it is. And so these are actually two problems: this flatness problem and the horizon problem that were solved in the 1980s, and they were solved by this thing called inflation. And so inflation is a pretty amazing thing. It has to do with quantum fluctuations. It's kind of a weird thing, but basically the idea is, I only have like a minute left in this video, but the basic idea is, in quantum mechanics, you can have energy coming from the vacuum of space, like from nothing, for a short amount of time. This is basically what happens is, during a very short time, during the grand unification epoch, the universe expands something like 10 to the 50th power in size. And that's a very nonlinear expansion in the very early universe, and that actually solves the problem of the horizon problem and the flatness problem. Okay, so that's basically, I mean, this, mathematically is